Today we'd like to look at the concept of symmetry. Symmetry occurs frequently in nature. A butterfly has wings that are symmetric to each other. Generally speaking, animals are approximately symmetric. They have one eye on each side of their face. Our hands are reflections of each other. If we see a bridge, usually one side of the bridge is the same as the opposite side if you look and compare it with the center line. We see symmetry quite a bit in architecture as well. Today we want to look at symmetry in mathematics and in our functions and equations. The first thing we want to look at is the graph of x equals y squared. And if we compare the point 4, 2 and 4, negative 2, we see these are reflections of each other across the x-axis. And so for any point xy, the point x and negative y would be a reflection across the x-axis. And so we would say 4, 2 and 4, negative 2, or the point x, y and x, negative y. These points are said to be symmetric with respect to the x-axis and are reflections of each other across the x-axis. And we'll find the same thing is true if we look at the graph of y equal to x squared minus 5. We find that that will go through the point 3, 4 and negative 3, 4. And if we draw this graph, we can see that these 2 points, negative 3, 4 and 3, 4, are equidistant from the y-axis. And any general point then x, y, and negative x, y, these 2 points would be reflections of each other across the y-axis also. And we would say 3, 4 and negative 3, 4, or x, y and negative x, y are symmetric with respect to the y-axis. And so these are reflections across the y-axis. And so we would say the whole graph then of this parabola here is symmetric with respect to the y-axis. And the previous one we looked at, the graph of this parabola is symmetric with respect to the x-axis. Now, if we look at another equation, y equal to x cubed, and we look at a point 2, 8 and a point negative 2, negative 8, And if we draw a few more points on here, we see that the point 2, 8 and the point -2, -8 are reflections of each other through the origin. And so we could pick any general point x, y, and a point -x, -y, and the same would be true, and so we could say the ordered pair xy and -x, -y are symmetric with respect to the origin. And so we could say the graph of y equal to x cubed is symmetric with respect to the origin. So far, what we've done is look at graphs and visually inspect them to see if they look symmetric with respect to either the x-axis, the y-axis, or the origin. There are also algebraic tests of symmetry. And let me spell that correctly. And so let's look at what these are, and then I'll give you examples of how they're used. So if we're testing or looking to see if a graph is symmetric with respect to the x-axis, we can say if replacing y with -y produces an equivalent equation, then the graph is symmetric with respect to the x-axis. And then similarly, for the y-axis, if replacing x with -x produces an equivalent equation, then the graph is symmetric with respect to the y-axis. And for the origin, if replacing x with negative x and y with negative y produces an equivalent equation, then the graph is symmetric with respect to the origin. So let's see how this works. Let's look at the first equation we saw a graph of, x equal to y squared, which was this horizontal parabola. And we saw that by visually inspecting that it looked symmetric with respect to the x-axis. And our algebraic test for that is to replace y with negative y. So let's replace y with negative y to test for symmetry with respect to the x-axis. And so we'll have x equals negative y in parentheses squared. And so if we simplify that, we get x equals y squared. And this is equivalent to the original equation. And so the graph is symmetric with respect to the x-axis. Okay, now let's test our second equation that we saw, which was y equal to x squared minus 5. And it seemed to be symmetric with respect to the y-axis. So let's replace, if you notice, it's the opposite variable if we're testing for symmetry with respect to the x-axis, as we did above here. We replace the opposite variable with its negative. Here we're testing for symmetry with respect to the x-axis, so we replace y. I don't think I said that right. We're testing for symmetry with respect to the y-axis, so we replace x with negative x. And so we'll have y equals negative x quantity squared minus 5. And if we simplify that, we get y equals x squared minus 5, which is equivalent to the original equation. And so the graph is symmetric with respect to the y-axis. Okay, so now let's look at the third equation we had, y equal to x cubed. And to algebraically show or test to see that it's symmetric with respect to the origin, we want to replace x with negative x and y both, and y with negative y. And so we'll have negative y equals negative x cubed, and that simplifies to negative y equals negative x cubed. And now, can we make this equivalent to the original? Well, yes, if we multiply both sides by negative 1, we get y equals x cubed, and then this is equivalent to the original equation, Therefore, the graph is symmetric with respect to the origin. Okay. Now let's take an equation that we haven't looked at yet. Let's look at 2x to the fourth plus 3 equals y squared. And the question or the directions will be determine whether the graph is symmetric with respect to the x-axis, y-axis, or the origin. So we want to apply those 3 tests to this one particular equation. Okay, so let's test for symmetry with respect to the x-axis. So that means replace y with negative y. Okay, so we'll have 2x to the fourth plus 3 equals negative y quantity squared. And that gives us an equivalent equation. So yes, we have symmetry with respect, I'm going to abbreviate WRT, with respect to the x-axis. And then let's test for the y-axis. So we'll replace x with negative x, and we get 2 negative x to the fourth plus 3 equals y squared, and that simplifies to 2x to the fourth plus 3 equals y squared. And so, yes, we have symmetry with respect to the y-axis. And then if we test for symmetry with respect to the origin, we'll replace x with negative x and y with negative y. And so we'll have 2 negative x to the fourth plus 3 equals negative y squared. And that simplifies to 2x to the fourth plus 3 equals y squared. So we have symmetry with respect to the origin. And let me share with you one more thing here. If we have any two of these symmetries, the third will automatically be symmetric also. Okay, so what I've done so I can show you that these are symmetric is I've taken this equation and I've written it with the y squared on the left. Y squared equals 2x to the fourth plus 3. And I've solved for y. And so I get plus square root of 2x to the fourth plus 3. And y equals negative square root of 2x to the fourth plus 3. And then I've graphed these. Let's see, hopefully you can see this. And we have the top half of the graph and the bottom half of the graph. And so you can see it's symmetric with respect to the y-axis, the x-axis, and the origin. So we were right in our test. Okay, so that's how we would test by plugging in to show symmetry with respect to the x-axis, with respect to the y-axis, and with respect to the origin. Now, let's look at just some points and some of the problems that we'll see in our homework assignment is to find the point that is symmetric to the given point with respect to the x-axis, y-axis, and the origin. So if I have the point -5, 6, it's helpful if we put that point on a graph. 1, 2, 3, 4, 5, -5, 4, 5, 6. And so here's our point. And so if we're looking for a point that's symmetric to this point with respect to the x-axis, we find the point on the opposite side of the x-axis and then just determine what the coordinates of that point are. Well, it will have the same x, so -5, but opposite sign for y, so -6. And then if we want the point that's symmetric to our original point with respect to the y-axis, we'll find that point opposite, equidistant, opposite the y-axis. And then what are the coordinates of that point? Well, instead of -5, it would be 5, but it will have the same y value, so 5, 6. And then if we want the point that's symmetric to our original point, symmetric with the origin, we find a point, go through the origin, equidistant on the other side of the origin, and we would have the same numerical values but opposite signs, and so we would have the point 5 and -6. Now, symmetry can also be used in determining whether a function is odd, even, or neither. So we want to see what that means. And so let's do this. Even and odd functions, and odd. Okay, so if the graph of a function f is symmetric with respect to the y-axis, we say that it is an even function. That is, for each x in the domain of f, f of x equals f of -x. And if we stop and think about that for a minute, if it's symmetric with respect to the y-axis, that means it's, to determine that in our testing, we changed the sign of the x value, and so that would make this equation true. F of x equals f of -x. And then if the graph of a function f is symmetric with respect to the origin, we say that it is an odd function. That is, for each x in the domain of f, f of -x equals negative f of x. So here we can think, well, we're changing both the sign of x and the sign of y, because f of x is just another way of writing y. So we would just use the same tests for symmetry with respect to the y-axis to determine if the function is even, and for symmetry with respect to the origin to determine if the function is an odd function. There is no term that would describe something that was symmetric with respect to the x-axis, because those graphs would not be even functions. Okay, so an example of this would be determine whether the function is even, odd, or neither, or we could say neither odd nor even. And so if we have the function f of x equals negative 3x cubed plus 2x, we would substitute y, first of all, negative 3x cubed plus 2x, and then to determine if it were even, we test for symmetry with respect to the y-axis, asking, is it even? And so we'll substitute x for, or negative x for x, so we'll have y equals negative 3 and then negative x cubed plus 2 times negative x. And let's simplify this. So if we cube negative x, we get a negative x cubed times negative 3 is 3x cubed, and then our next interval is interval D, and so let's choose positive 1/2 there. And so our first number will be 1/2, and then if we plug it in, we'd have 1/2 plus 1/2, or 3/2, and then 1/2 minus 2/2 is minus 1/2, and then 1/2 plus 2 is 5/2, and then 1/2 minus 4/2 is minus 3/2. And if we multiply all that out, we should get a positive 45 over 32, which is approximately 1.4, and that's positive, so our graph should be above the x-axis. Okay, and then in interval E, we would have the test point 1.5 or 3/2. So if we plug that in, we'll get 3/2, and then 1/2, 3/2 plus 1, no, 5/2 plus 1, 5/2, and then 3/2 minus 1 is 1/2, and then 3/2 plus 2 or 4/2 is 7/2, and then 3/2 minus 4/2 is minus 1/2. And so if we multiply all those out, we should get the same number that we have up here, but this will be negative, or approximately negative 1.4, so that's negative. So our graph is below the x-axis. And then finally, in interval F, let's pick 3. And so if I plug that in, I get 3, and then 3 plus 1 is 4. 3 minus 1 is 2. 3 plus 2 is 5. And 3 minus 2 is 1. So if I multiply all those out, I get a positive 120, so that's positive, and our graph is above the x-axis. Okay, so let's take a minute and graph this. And so we put our zeros on here. Negative 1, negative 2, positive 1, and positive 2. And then we can use the values that we found in each of these intervals. And in interval A, at negative 3, let's say negative 50, negative 100, negative 150. Okay, so at negative 3, we're approximately negative 120, which would be about here. And then we go up to here. And then in interval B, we picked negative 3/2, and we got approximately 3.3. So if this is positive 50, this is just barely above the axis. And then in interval C, we got a negative 1.4, which is even closer to the x-axis. And then in interval D, we got positive 1.4. In interval E, we got a negative 1.4. Wait a minute. I'm missing something here. 35. Oh, wait. This one should be negative 105 over 32, or approximately a negative 3.3. Sorry. So negative 3.3 right here. So it's kind of mirroring these two intervals here have similar heights. These two intervals here have similar heights, and then the two out here. So at positive 3, we have a positive 120, and so that would be approximately right here. So the graph goes up, and then the maximum isn't at the middle point here. I checked that out by graphing on my old calculator. And you can always check this on your calculator to see how close you got. Okay, so this is negative 2. Okay, so this is an approximate graph of our function h of x equal to x times x squared minus 1 times x squared minus 4. Okay. Right. I'd like to ask you if there are any questions, but you can always email me if you have questions. And let's go on then and look at another graph. And we have another equation that I want to graph. If I can find it. Here we go. We have g of x equal to x minus 2 to the third power times x plus 3. Okay, so we have a degree of 4, and so that's even, and our leading coefficient, so we're looking at n behavior, and our leading coefficient is positive, so that means we'll have a graph that looks something like this. Both ends will go up. Okay, then let's find our zeros. So we'll set our function, our y value equal to 0, f of x equal to 0, and then solve. And we get x minus 2 cubed equal to 0, so x minus 2 equals 0, and x equals 2, and that's multiplicity of 3. And so our graph will go through the x-axis at 3, and then set, multiplicity 2 at 3 at 2. And then x plus 3 equals 0, and so x equals negative 3, and that's multiplicity 1. And so that's odd. And so again, the graph goes through the x-axis. Okay, next let's find our y-intercept. So we let x equal 0. And so our y, if x is 0, we'll have 0 minus 2 quantity squared cubed times 0 plus 3. So negative 2 cubed times 3, so negative 8 times 3, or negative 24. So our y-intercept is 0, comma, negative 24. Okay, so let's do our table again. Our zeros are 2 and negative 3. Let's do our table again. Let's rewrite our function so we have it in front of us. X minus 2 cubed, x plus 3. And let's draw our number line with zeros at negative 3 and 2. And so this divides the number line into the intervals negative infinity to negative 3, negative 3 to 2, and 2 to positive infinity. So let's call those A, interval B, and interval C. And let's do our table again. A, B, C. test point. And evaluation. And then positive or negative. And then above or below the x-axis. Okay. So in interval A then, let's pick -4. And if we plug that in, we'll have -6 cubed times -1. And just use your calculator. -6 cubed is times -1 is positive 216. So that's positive, and that means our graph at in that interval is above the x-axis. Okay, so in interval B, that includes 0, so let's pick 0, and we found that that was -24, so that's negative, and so our graph is below the x-axis. And then in interval C, let's pick 3, and then if we plug that in, we'll get 1 cubed times 6, or 6. And that's positive, so the graph is above the x-axis. Okay, so let's draw our graph. Okay, let's call this 100, 200, so 50, 250, and so we'll have -1, -2, -3, and +1, +2. Okay, so we picked -4 and we evaluated that at positive 216, so that'd be approximately right here. And then we picked 0, and that was, so -50, -100. So that was approximately right here at 0 and -24. And then we picked 3, and we got 6, so that was approximately right here. Okay, so we're not sure what happens between -3 and 2, so I found some more values, which is what's suggested if we can't really tell what the graph is going to look like. And so I'm going to pick -2, and at -2 we got -64, and so that's about right here. At -1 we got -54, which is about right here. And then at 0, of course, we have -24. And at 1, we got -4. So we have a little better idea. I also found, I put this in my calculator, and found the minimum point at -1, which is at -1 and 3/4. And that's just a hair below this one. So our graph is going to go like this. And then over. If we stretch this, it would seem like it went down a lot further than it does. So this is the minimum point at negative 1.75 and negative 66 approximately. Okay, so this one, in order to find the way this looked, we needed to plot a few extra points as is suggested in step number 4 to determine what the graph actually looks like. Okay. So we've done 3 graphs. Let's also look at one other thing that we have, and that is called the intermediate value theorem. Intermediate value theorem. And that helps us to be able to determine if there's a 0 between any 2 numbers. And so let's look at what this says, and then I'll give you an example. For any polynomial function p of x with real coefficients suppose that for a not equal to b, p of a and p of b are of opposite signs. Then the function has at least one real 0 between A and B. The intermediate value theorem cannot be used to determine whether there is a real 0 between A and B when P of A and P of B have the same sign. Okay, so what this is saying is, suppose we have a graph and here's a part of our function. Okay, let's say here's A and here's B. If I find the y value for this A, I would come over here to the y-axis, and this is P of A. If I find the y value for B, then I come down to this point and go over to the y-axis, and here's P of B. So at A, the graph is, in this case, above the x-axis, and over here at B, the graph is below the x-axis, which means that P of A here is positive and P of B here is negative, which means the graph had to have crossed the x-axis somewhere between A and B, if these have opposite signs. It says at least one real zero between A and B. And then if we call that C, then we could use further knowledge to find that if we'd like. But what we're looking for is, if we're given like two consecutive numbers, is there a zero between those two numbers? So let's look at a problem. This is number 39 in your book. F of x equals x cubed plus 3x squared minus 9x minus 13. And the directions will say, use the intermediate value theorem to determine, if possible, whether the function has at least one real zero, between A and B. Okay, so for this problem, we're given A equal to -5 and B equal to -4. Well, if you recall, a real easy way to evaluate a function at a specific number is to divide synthetically, and P of whatever number we use is equal to the remainder. Okay, so we divide 1, 3, -9, -13 by -5. So bring down the 1. 1 times -5 is -5. Add, we get -2. -2 times -5 is 10. Add, we get 1. 1 times -5 is -5. Add, we get -18. So here, P of -5 equals -18. And then we want to divide by -4 and see if we get a remainder that has the opposite sign. So bring down the 1. 1 times -4 is -4. Add, we get -1. -1 times -4 is 4. Add, we get -5. -5 times -4 is 20. Add, we get 7. So P of -4 equals 7. And so we would say, since the function value changes sign between -5 and -4, there is at least one real zero between -5 and -4. Okay, so that's an example of that. Let's try another one. Number 40, same directions. F of x equals x cubed plus 3x squared, same function, minus 9x minus 13, but this time let's look between 1 and 2. So we'll divide by 1. 1, 3, negative 9, negative 13. So bring down the 1. 1 times 1 is 1. Add, we get 4. 4 times 1 is 4. Add, we get negative 5. Negative 5 times 1 is negative 5. Add, we get negative 18. So P of 1 equals negative 18. And then let's divide by 2. 1, 3, negative 9, negative 13. Bring down the 1. 1 times 2 is 2. Add, we get 5. 5 times 2 is 10. Add, we get 1. 1 times 2 is 2. Add, we get a negative 11. So P of 2 is negative 11. Since the function did not change sign, between 1 and 2, we cannot determine or let's say the intermediate value theorem cannot be used to determine whether there is a 0 between 1 and 2. Okay, so that's how we'd use the intermediate value theorem. And that's the end of section 8.2. We'll look a little bit further in 8.3 and look at some other things that we can find from our polynomials. Meanwhile, have a good day.